Hello there, and welcome to your nightly deep dive into the science of sleep. Tonight, we turn our gaze outward, not just to the stars, but to the silence between them. The universe is vast and ancient and filled with the kind of quiet that makes you wonder whether anyone else is out there listening to it. That question has haunted scientists and philosophers for decades now, not because it is unanswerable, but because the answer, whatever it turns out to be, will reshape everything we think we know about our place in the cosmos. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, though, all you need to do is settle in. Let your shoulders soften and your breathing slow. Allow the thoughts of the day to loosen their grip, one by one, the way a hand opens slowly in the warmth. Your mind can begin to unwind. There is nothing that needs solving tonight, nothing that requires your full attention, just the quiet hum of the universe and the steady rhythm of your own breath, and a few remarkable ideas to carry you gently towards sleep. Let's begin. There is a question so simple, it sounds almost childlike, and yet it has never been fully answered. In 1950, a physicist named Enrico Fermi was having lunch with colleagues at the Los Alamos National Laboratory in New Mexico when the conversation turned to a news story about UFO sightings. Fermi, who was one of the most brilliant minds of the 20th century and the man who had built the world's first nuclear reactor, listened patiently to the discussion and then asked something that stopped the table cold. He looked up from his meal and said, "In essence, where is everybody?" The universe, Fermi reasoned, is approximately 14 billion years old. It contains hundreds of billions of galaxies, each holding hundreds of billions of stars. Many of those stars have planets. Some of those planets must be similar to Earth. And yet, despite all of that time and all of that space, we have detected no signal, no visitor, no unambiguous sign of another civilization anywhere. The numbers, when you do the arithmetic, suggest that the galaxy should be teeming with intelligent life. The silence, by contrast, is absolute. That gap between expectation and observation is what scientists now call the Fermi Paradox, and it is one of the deepest, most beautifully unsettling puzzles in all of science. What makes this so fascinating is that the paradox is not a failure of imagination. It is a failure of evidence, and those two things are very different. We are not struggling to think of reasons why life might exist out there. We are struggling to explain why, if it does, the cosmos is so completely, profoundly quiet. The paradox has a mathematical backbone that most people never see, and it makes the silence even harder to explain. In 1961, an astronomer named Frank Drake sat down and wrote what he called an equation, though it is less a traditional equation and more a structured way of thinking through probabilities. The Drake equation, as it has been known ever since, breaks the question of intelligent life in the galaxy into individual factors and multiplies them together. You start with the rate at which new stars form in the Milky Way each year, which astronomers have measured at somewhere between 1 and 3 new stars annually. Then you multiply by the fraction of those stars that have planets orbiting them, which we now know from missions like Kepler to be astonishingly high. Perhaps as many as 3/4 of all stars host at least one planet. Then you factor in the number of planets in each system that might support life, the fraction of those that actually develop life, the fraction where life becomes intelligent, the fraction that developed detectable technology, and finally the average length of time such a civilization broadcasts signals into space. When astronomers plug in even modestly optimistic estimates for each of these factors, they get a number far greater than one. They get thousands, sometimes millions of potential civilizations in the Milky Way alone. And yet, the universe sends back only silence. The remarkable part is that even if you are deeply conservative with every single estimate, even if you assume life is rare, intelligence rarer still, and technological civilizations brief, the sheer age and size of the galaxy still suggests we should have found something by now. One of the most popular proposed solutions to the Fermi Paradox is also one of the darkest, and it carries a warning that some scientists believe we should take very seriously. It is called the Great Filter, and it was first articulated by the economist and philosopher Robin Hanson in 1998. The idea is this: somewhere along the path from simple chemistry to a civilization capable of spreading across the stars, there is a barrier so difficult to cross that almost no species ever makes it. Something filters nearly everyone out. The question, and it is a deeply uncomfortable one, is whether that filter lies behind us or ahead of us. If the filter is in our past, if the truly improbable step was, say, the emergence of the first self-replicating molecule, or the leap from single-celled life to complex multicellular organisms, then we may have already survived the hardest part. We might be rare survivors, the few who made it through, which would explain the silence around us. But if the filter lies ahead, if civilizations routinely reach our level of technology and then collapse, whether from war or ecological failure or something we have not yet imagined, then the silence around us is not a testament to our rarity. It is a warning about our future. The implications are staggering because they run in both directions at once. What makes this compelling is that every piece of evidence that suggests life is common elsewhere, every newly discovered planet in a habitable zone, every prebiotic molecule found in interstellar space, actually makes the ahead filter scenario more terrifying, not more reassuring. The more inevitable life seems, the more something else must be culling it before it reaches the stars. The discovery of extremophiles on Earth has quietly shifted the conversation about where life might exist, and it has made the silence simultaneously easier and harder to explain. An extremophile is an organism that thrives in conditions that would kill most living things. They are not hypothetical. They are everywhere. And they are real. Bacteria have been found flourishing inside the cooling towers of nuclear reactors, absorbing radiation that would be lethal to a human in seconds. Other microbes have been pulled from ice cores drilled 2 miles beneath the surface of Antarctica, alive and metabolizing slowly in water that has not seen sunlight for hundreds of thousands of years. Organisms called tardigrades, microscopic animals barely 0.5 millimeter long, roughly the size of a period at the end of a sentence, can survive the vacuum of space, extreme radiation, and temperatures ranging from close to absolute zero to well above the boiling point of water. These discoveries have forced biologists to expand dramatically their definition of a habitable environment. Moons like Europa, which orbits Jupiter and is entirely covered in a shell of ice, but harbors a liquid ocean beneath it, suddenly look not just possible, but plausible as homes for microbial life. Enceladus, one of Saturn's moons, actively vents water vapor and organic molecules into space from cracks in its frozen surface. These places seemed lifeless a generation ago. They no longer seem that way. The fascinating part is that the same discoveries that expand the range of places life might exist also deepen the paradox. Because if life is this resilient and this resourceful at finding footholds, then the galaxy should be bursting with it, and its silence becomes more, not less, difficult to understand. Some researchers now argue that the most likely solution to the Fermi Paradox is not that civilizations are absent, but that we are simply not listening in the right way. This is sometimes called the zoo hypothesis, or more broadly, the observation problem. The idea begins with a straightforward technical point: the electromagnetic spectrum. The full range of wavelengths at which information can be transmitted through space is enormous. Radio waves, which are the primary focus of SETI, the search for extraterrestrial intelligence, represent a tiny sliver of that spectrum. Even within the radio band, we have only surveyed a fraction of the frequencies, a fraction of the sky, and a fraction of the possible signal types that an alien civilization might use. A civilization even a few centuries more advanced than ours might communicate using neutrinos or quantum entangled particles, or some channel of physics that we have not yet discovered and cannot yet detect. Expecting to intercept their communications with our current equipment is a little like trying to receive a modern broadband fiber optic internet signal using a tin can on a string. The equipment is simply not matched to the signal. Carl Sagan made a version of this argument in his novel Contact, where he suggested that civilizations encode themselves in places we might not think to look, in the mathematics of prime numbers, or in the structure of pi itself, which is a thought so layered and strange that it lingers long after you first encounter it. What makes this so gripping is that the absence of a signal is not the same as the absence of a sender. Silence in one frequency is not silence in all frequencies, and the history of astronomy is largely a story of how each new instrument we build reveals a universe that had been broadcasting all along in wavelengths we simply could not hear. There is a related idea that goes even further, suggesting that contact has already happened, just not in any form we recognized. This is sometimes called the interstellar artifact hypothesis, and it holds that advanced civilizations, rather than broadcasting signals into the void and waiting decades for a reply, might instead send physical probes into the galaxy, automated, self-replicating spacecraft that arrive at promising star systems, observe quietly, and either report back or wait. The mathematician John von Neumann showed in the 1940s that a self-replicating machine is theoretically possible, and later calculations suggested that a fleet of such probes, even traveling at a modest fraction of the speed of light, could survey every star system in the entire Milky Way within a time frame shorter than the current age of the galaxy, which raises an unsettling possibility. If such probes exist, one or more of them could already be here. The solar system is large and mostly uncharted. We have visited fewer than a dozen of the billions of objects that orbit the Sun. The 2017 object known as Oumuamua, the first interstellar object ever observed passing through our solar system, moved in ways that puzzled astronomers, accelerating as it departed in a manner that could not be fully explained by known physics. Most researchers now attribute this to an outgassing of material from a comet-like interior, but the brief, heated debate it sparked was a window into how genuinely open this question remains. The deeper fascination is that we are extraordinarily young as a technological species. We have been broadcasting radio signals into space for barely a century, which on the cosmic timescale is less than an eye blink. Any probe sent by a civilization that arose a billion years before us would have had to be extraordinarily patient, sitting in silence, waiting for someone young enough to stumble into the game. One of the most intellectually provocative proposed solutions suggests the paradox dissolves entirely once you consider what a sufficiently advanced civilization would actually want to do. This is the idea of the transcension hypothesis, proposed by the futurist John Smart, and it runs against almost every intuitive assumption about what an advanced species would do with its capabilities. The standard image of a galactic civilization, the one embedded in Star Trek and Star Wars, and the dreams of 1,000 science fiction writers, is one that expands outward, colonizing star after star, spreading across the galaxy like a great slow tide. But Smart argues that this gets it exactly backward. He suggests that as civilizations become more sophisticated, they invariably turn inward rather than outward. They miniaturize, they optimize, they explore the universe not at large scales, but at the smallest scales imaginable, building increasingly dense and complex computational and physical environments at the nanoscale and below, effectively creating vast inner universes of experience and thought within volumes smaller than a grain of sand. Under this model, the Milky Way is not quiet because it is empty. It is quiet because every civilization in it has already retreated to the inside, building realities of unimaginable richness that are invisible to observers on the outside. They are not gone. They are just looking in a different direction entirely. The wonder comes from recognizing that if the transcension hypothesis is correct, the universe may be extraordinarily crowded with intelligence, just not in any form or at any scale that our current instruments could detect. The silence would then be not an absence, but a redirection. The universe turning itself inward with the patient thoroughness of a mind that has all of time and needs none of our space. The possibility that life is common but intelligence is rare represents one of the most debated dividing lines in the entire Fermi Paradox literature. Biologists have long argued about whether intelligence, the kind that builds tools, tells stories, and eventually constructs radio telescopes, is an inevitable product of evolution, or whether it is a spectacular accident. On Earth, life arose relatively quickly after the planet cooled enough to support it. The first microbes appeared roughly 3.5 billion years ago, perhaps even earlier. But complex multicellular life did not appear until about 600 million years ago. And large-brained, socially complex animals capable of abstract reasoning have been here for only a tiny sliver of that time. This uneven timeline suggests that the early steps, the chemistry, the self-replicating molecules, the first cells, may not be the hard part. The hard part may be the transition from simple life to complex life, or from complex life to minds that can contemplate their own existence. The paleontologist Peter Ward and the astronomer Joe Kirschvink have argued that the evolution of the eukaryotic cell, the kind of cell with a nucleus, the building block of every plant and animal on Earth, was a contingent accident that required a specific, improbable collision of a particular kind of bacterium with a particular kind of archaeal host, and that without it, life on Earth might still be nothing but a thin film of microbes on rocks at the ocean floor. If they are right, then the galaxy could be brimming with that thin film and utterly bereft of anything more complex, which would explain the silence rather neatly, but would not make it any less lonely to contemplate. This is one of the reasons the Fermi Paradox is more than an abstract puzzle. It is a mirror that we hold up to our own existence, and when we look into it honestly, what we see is how improbable, how fragile, and how quietly astonishing it is that we are here at all. There is a version of the solution to the Fermi Paradox that lives not in astrophysics or biology, but in the mathematics of timing. And it suggests that the silence might not be about absence at all. It is called the rare earth hypothesis in some formulations, and the timing argument in others. And it begins with the observation that the universe was not always a hospitable place. In its first few billion years, the Milky Way was a far more violent environment than it is today. Supernovae were more frequent. Gamma-ray bursts, pulses of radiation so intense they can sterilize an entire hemisphere of a planet from thousands of light years away, erupted across the galaxy with a regularity that made complex life survival statistically difficult. The galactic center, where stars are densely packed, experienced gravitational disruptions that would have sent comets and asteroids raining into planetary systems at devastating intervals. Researchers Piero Madao and others have modeled the emergence of what they call a galactic habitable zone, a ring of space within a galaxy at just the right distance from the center to avoid lethal radiation, but close enough to contain the heavier elements forged in earlier stellar generations. Our solar system sits in this zone, and it has been here long enough, about 4.5 billion years, for life to get a foothold, develop complexity, and produce a species now standing in the dark and wondering if anyone else made it. If that combination of location and timing is rarer than we typically assume, then the answer to the Fermi Paradox might simply be that we are early, not uniquely special, not cosmically privileged, just early arrivals to a universe that is still in the process of becoming habitable, a universe where the great flowering of civilizations, if it comes at all, may lie billions of years ahead of us still. What makes this so captivating is the image it conjures. A galaxy, not empty, but simply quiet with youth. The civilizations that will one day fill it, not yet born, not yet looking up at their own night skies and asking the same questions we are asking tonight. Some of the most serious researchers in the field now believe that the Fermi Paradox is best understood not as a single problem, but as a cluster of different problems that have been mistakenly fused together. This view, associated in part with the philosopher Milan Cirkovic, suggests that the paradox assumes a series of things that may each be individually wrong. It assumes that civilizations expand outward in ways we would recognize and detect. It assumes that the timescale on which we have been looking, essentially the past 70 years of radio astronomy, is in any way meaningful relative to the age of the galaxy. It assumes that we understand what counts as a signal. It assumes that other civilizations would want to communicate with a species at our level of development, which is a bit like assuming that a marine biologist would want to have a lengthy conversation with a bacterium. And it assumes that non-detection equals absence, which is the most basic logical error in science. When you disentangle these assumptions and examine each one separately, the paradox begins to dissolve. Not because there is a single elegant answer, but because it was never quite as unified a mystery as it appeared. The silence of the universe might be the product of many different factors, stacking quietly on top of one another. No single one of them sufficient, but all of them together enough to account for what we observe. This is, in its own way, a more honest and more rigorous answer than the dramatic ones. It lacks the narrative tidiness of a great filter or an alien zoo. But science rarely delivers tidiness. It delivers complexity, slowly. That contrast is in many ways the central lesson of the Fermi Paradox as a scientific inquiry. The question sounds simple. The answer, it turns out, is made of everything we do not know. And the list of things we do not know about the universe is still very long. There is one proposed explanation for the Fermi Paradox that carries a peculiar kind of irony, because it suggests that the very act of searching might itself be the reason no one calls. This is sometimes called the dark forest theory, popularized by the Chinese science fiction author Liu Cixin in his trilogy that begins with the three-body problem, though the underlying logic predates the fiction. The argument is this: in a universe of finite resources and uncertain intentions, any sufficiently advanced civilization has strong incentive to remain undetected and to eliminate any civilization it detects before that other civilization can grow powerful enough to become a threat. Under this model, the galaxy is not a community waiting to welcome newcomers. It is a dark forest in which every hunter moves in total silence, because any sound, any broadcast, any signal, any illuminated city glimpsed from orbit is an invitation to be destroyed. The civilizations that survive are the ones that went quiet long ago. The ones that broadcast their existence are the ones that are no longer here. If this sounds extreme, it is worth noting that it is the exact logic that governed nuclear deterrence for half of the 20th century. The safest posture is silence and uncertainty, because transparency invites attack. Liu Cixin took this logic and scaled it to the cosmos, and the result is one of the most unsettling ideas in all of science fiction, made more unsettling still by the fact that it is not really fiction. It is a reasoned extrapolation from game theory and resource scarcity, and it has no easy refutation. The fascinating part is that this theory, if true, would mean that our early radio broadcasts, those century-old transmissions of television signals, military radar, and the occasional deliberate message aimed at star clusters, have already announced our presence to whatever is out there, and that the silence we are hearing in return is not indifference, but something more deliberately patient. And yet, the search continues, because the alternative to searching is a kind of resignation that does not sit easily with the curious mind. The SETI Institute, based in California, has been scanning the skies for anomalous signals since the 1980s. Projects like Breakthrough Listen, launched in 2015 with a $100 million commitment from the investor Yuri Milner, represent the most comprehensive search for extraterrestrial intelligence in history, scanning millions of star systems across a broad range of radio and optical frequencies. The Allen Telescope Array in Northern California operates continuously, cycling through target lists that now include not just nearby sun-like stars, but also stars known to have planets in their habitable zones, as identified by the Kepler and TESS space telescopes. In 2020, a signal known as BLC1 briefly excited astronomers. It appeared to originate near Proxima Centauri, the closest star to our Sun at just over 4 light-years away, and it had the narrow bandwidth and frequency drift that researchers associate with a technological source. Months of careful analysis ultimately attributed it to terrestrial radio frequency interference, almost certainly from human-made equipment here on Earth. The episode illustrates both the extraordinary sensitivity of modern search equipment and the equally extraordinary caution required to distinguish a genuine signal from the noise of a technologically saturated civilization doing the searching. We are, in a very real sense, trying to listen for a whisper while standing in the middle of a crowd. The deeper fascination is that every disappointment, every signal that turned out to be terrestrial in origin or easily explained by natural astrophysics, has made the search more rigorous rather than less meaningful. The null result, the absence of detection, is itself data, and it slowly, patiently, narrows the space of possible explanations. Now, as the night deepens and the questions settle around you like a soft and patient dark, it is worth considering not just the science of the paradox, but what it means to be the kind of creature that asks it at all. We are, as far as we know, the only species on this planet that looks up at the sky and wonders whether it is alone. Other animals are aware of their surroundings with extraordinary precision. Birds navigate by magnetic fields and star patterns. Whales communicate across ocean basins in frequencies we are still learning to decode. But no other species on Earth has yet built a radio telescope, aimed it at a distant star, and waited in the quiet for an answer that may take generations to arrive, if it arrives at all. That capacity for patient, hoping curiosity is one of the most remarkable things about being human. It is not obviously useful in the short term. It does not fill a stomach or mend a wound. It is the kind of thinking that exists at the edge of what biology alone would produce, reaching for something that transcends immediate survival and asks simply, is there anyone else? There is something deeply moving about the fact that in the middle of all the noise and difficulty and beauty of ordinary human life, we find the time to listen. What makes this so deeply meaningful is that the act of asking the question, honestly, rigorously, with instruments and mathematics and the full weight of scientific method, is itself a kind of answer. It says that intelligence, when it arises, tends toward curiosity rather than incuriosity, toward connection rather than isolation, toward the long reach rather than the near horizon. And whatever the universe eventually reveals about whether we are alone, that tendency seems worth honoring. The Fermi Paradox, at its deepest level, is not really about aliens. It is about time. 14 billion years is a number so large that it resists genuine comprehension, the way an ocean resists being held in a cupped hand. But try, for a moment, to inhabit even a small portion of that scale. The Milky Way formed roughly 13 billion years ago. For the first several billion years, it was a harsher place than it is now. Metal poor, energetically violent, hostile to the delicate chemistry that life requires. By the time conditions became broadly favorable, by the time solar-type stars in stable galactic orbits had enough heavier elements to build rocky planets with liquid water, our sun had not yet ignited. It came to life about 4.5 billion years ago, already a late-generation star, forged from the recycled remnants of older stellar generations that had lived and died before it. Life appeared on Earth with what seems, in retrospect, like almost suspicious speed, within a few 100 million years of the planet's surface, cooling enough to hold water in liquid form. And yet, intelligence, the kind that wonders about itself, took another 3.5 billion years to emerge. 3.5 billion years of patient, unhurried evolution. Oceans of time, layer upon layer of biological change, most of it invisible and slow, accumulating with the steadiness of sediment on the ocean floor. When you sit with that span of time honestly, the silence of the universe starts to feel less like an absence and more like a very long pause in a very old conversation. The remarkable part is that we are the conversation. We are the moment in the cosmos when matter became curious about itself, when the universe began to ask what it is. That is not a small thing. It is perhaps the largest thing there is. The most honest answer to the question of whether we have finally found a solution to the Fermi Paradox is that we have found many partial answers and no single complete one, and that this is exactly where science lives. The great filter, the rare earth, the timing argument, the transcension into inner space, the dark forest, the detection problem. Each of these is a legitimate and serious attempt to explain the same set of observations. Each captures something real. Each leaves something unexplained. The true solution may be a combination of many of them, stacked quietly in the dark like layers of sediment, each contributing a little to the silence that surrounds us. What the search has revealed in the decades since Fermi asked his lunch table question is that the universe is ancient and strange and endlessly patient, and that we are very young within it. The absence of contact may mean many things. It may mean we are alone, or nearly so, the luminous exception in a vast and sleeping cosmos. It may mean we are early, the first notes of a symphony whose full score has not yet been written. It may mean we are not looking in the right way, or the right direction, or the right dimension of experience. Or it may mean something we have not yet thought of, some answer that will seem, in retrospect, as obvious as the question that preceded it. The search continues, not because we expect to find the answer tomorrow, but because the asking of the question is itself an act of extraordinary courage and hope. We send our signals into the void, not knowing if anyone will hear them, and we listen in the dark, not knowing what we might hear in return. And somehow, that patience, that willingness to wait across distances of light years and timescales of generations, is the most human thing of all. The fascination lies in recognizing that the question Fermi asked over a lunch table more than 70 years ago has not diminished with time. It has only grown larger, more layered, more luminous at its edges, like a star seen more clearly as the atmosphere between us slowly clears. As we come to the end of our journey tonight, we have drifted through one of the most ancient and quietly urgent questions that science has ever carried. We have floated past the arithmetic of distant suns and the vast improbability of complex minds. We have watched civilizations rise and fall in theory, traced the edges of what we can detect and the deeper shores of what we cannot, and followed the patient logic of scientists who spend their lifetimes listening to a universe that may or may not be listening back. We have moved through silence and found it rich with meaning, full of possibility, full of the kind of wonder that does not resolve into easy answers, but deepens slowly, the way the night sky deepens the longer you look at it. If you enjoyed this journey, you might like to tap like or subscribe, or leave a comment with the part that surprised you most. It helps the channel reach more curious minds, and it keeps these long night voyages going. Let your jaw unclench now, and your shoulders drop another degree. Let your breathing find its easy, unhurried rhythm, the kind of breathing that belongs to sleep. The questions we have explored tonight are not going anywhere. They will be here tomorrow, patient and vast and ready. The weight of the day has eased, Your thoughts are growing lighter, loosening their grip on the edges of the evening. The night is doing what it does best, wrapping everything in a soft and generous dark. The silence around you now is not empty. It is full of rest, full of the quiet that comes after a long, curious journey through ideas that are bigger than any single mind. Let yourself sink into that silence. Let it carry you. Sleep well and good night. And if you happen to still be awake, there will be another video waiting on screen, ready to carry you onward into the night.